All right, welcome to Physics Video 8.3. The main focus of this video is going to be the concept of resonance. We're also going to learn about interference. These are both really quick topics. We need to know interference for the next video, so I figured I would just combine them. They don't really have a whole lot to do with each other. So first half of the video is about resonance, second half is about interference. Objectives are right there. Here we go. All right, so resonance requires us to understand three definitions, the last one being resonance. Before we can learn about resonance, we need to learn about what's called a forced vibration. Forced vibration, this is a term used by Paul Hewitt, the author of your book. It's not something I've seen in other places. It's one of those things that it's almost so silly to give it, it's almost silly to give it its own term because it happens so often. But it gives us a simpler definition for resonance. So anyway, here's the deal. Forced vibration. It occurs anytime the vibrations of one object forces another object to vibrate. And it happens all the time. All right, right now you're able to hear me. And the reason for that is in your earphones or speakers or whatever you're listening to me on, there's a little cone in there that vibrates. That causes the air to vibrate. So the vibrations of the speaker cone force the air to vibrate. Taking that another step, the air then forces your eardrum to vibrate. So that's another example of a forced vibration. The air molecules are vibrating back and forth. That forces your eardrum to vibrate. Okay. Guitar string, anytime you pluck a guitar string, you're forcing the strings, the body of the guitar that the string is attached to vibrate. Water wave. If you picture a water wave hitting, the beach or hitting a wall or whatever, when the wave hits the wall or the beach or whatever, it's going to cause the sand or the wall or whatever to vibrate too. If a duck is floating in the water floats up or vibrates up and down. That causes the duck to vibrate up and down. Air molecules from a thunderclap. If thunder's loud enough, it'll, if you're sitting at your dining room table, doing homework, and there's a loud thunderclap, you might notice water in your glass vibrate. That's another example of forced vibration. The air is vibrating, that causes the water to vibrate. Okay, so that's all forced vibrations are. Okay, the second thing we need to talk about is what's called natural frequency. I'll show you this a little bit better in class. I'll do a quick demo that'll show you this. But basically, the idea here is if an object is pushed or pulled, but just very briefly by an external force, it's going to vibrate, and the frequency that it vibrates at is called natural frequency. All right. For example, swings. Every swing on a playground has its own natural frequency. It turns out that natural frequency is determined by the length. All right. That's why when you're in elementary school, it's easy to line up with somebody else on a swing, right? You get on whatever you call it, a love line, or you're married, or whatever you call it when you're lined up on the swings so that you're swinging in unison with somebody. It doesn't matter, if you're really big and the kid next to you is really small, or one kid's swinging higher and the other kid's swinging lower. It's possible for you to all sort of swing in unison so that you're, all crossing the bottom point at the same time. That's because the frequency that swing wants to go back and forth at is determined just by the length of the swing. Okay. If you pluck a guitar string, a lot of you, know music and can hear a string plucked and tell which string it is just by the sound it makes. That's because each string has its own natural frequency that it wants to vibrate at. When you tighten or loosen the string, you're just changing the natural frequency. The tighter you make it, the higher the natural frequency is. And so when you pluck that string, the frequency that it vibrates at is called its natural frequency. And similarly, if I stand in my classroom and drop a quarter and a wood block, you can definitely tell which one's the quarter and which one's the wood block just based on the sounds that they make, because they have their own natural frequency that they sort of want to vibrate at. Okay, so resonance combines these two ideas. So before you move forward in the video, make sure that you understand those two ideas. Natural frequency is the frequency that an object wants to vibrate at. Forced vibration is when one object vibrates causing a second object to vibrate. All right, resonance occurs when the two things match up. All right, resonance occurs when the frequency of a forced vibration matches an object's natural frequency. All right, and what happens then is what's called resonance. The result is the amplitude of the object's vibrations are going to get bigger and bigger and bigger, up to a certain limit. All right, the coolest and easiest example, and I'll show you this in class, is pushing a kid on a swing. So that swing wants to swing back and forth. All right, so let's say that you push a kid on a swing and he starts swinging back and forth whatever, once every 4 seconds. Okay, we'll stick with that. Once every 4 seconds. All right. So if you want the kid to go higher, you got to give them a push, right? You got to give them regularly timed pushes. So, but the frequency that you need to push the kid at is the same as the frequency that the swing wants to swing at. So what do? You push the kid forward, he swings out, comes back, push. Out, back, push. Out, back, push. So the frequency at which the kid goes out and back on the swing set matches the frequency that you're pushing at. Okay? So that's an example of resonance. With every push, the kid goes higher. Pumping your legs on a swing. After you're old enough and learn how to pump your legs, you can go higher on a swing that way. There, your legs are the forced vibration. Your legs are vibrating back and forth. That forces the swing to vibrate. And if you do it at exactly the right frequency, every time you pump your legs, you go a little bit higher. So the frequency that you're pumping your legs at has to match the natural frequency of the swing. All right, you may have seen or heard about people breaking windows or wine glasses or something with a really loud sound or with their voice. It turns out it's not just the volume of the sound that matters, it's also the frequency of the sound.
Now we're going to time warp at 10,000 frames per second to see how sound waves destroy a glass. Jamie Vendera is famous for using the sound of his voice to destroy wine glasses. They seem to simply explode. But what's happening?
I know the sound waves broke the glass, but I couldn't see how. So I'm going to use our slow motion camera to see what we were missing. Instead of singing, I'm going to use a speaker and a tone generator. I have to find the natural vibrating frequency of the glass. I have to match this tone. That's it.
This is the exact tone to make this particular glass vibrate. When the tone is loud enough, the glass will shatter.
I can feel the glass shaking, but I can't see it. If I add a straw, then it's more obvious.
So what's happening here? The straw gets tossed side to side, but I can't see why.
Let's record it while I crank the volume. Alright, I took 10,000 frames per second, and I took 1 second. If I were to play back this whole video, it would take 8 minutes to get through.
Oh, this is amazing. What felt like the whole goblet vibrating is actually the rim bending back and forth, 337 times a second, the same rate as the sound waves. If I draw in the sound waves, you can see what's happening. One wave comes out of the speaker and pushes the side of the wine glass. The glass bounces back just when another sound wave pushes it again. If the timing or frequency of the sound waves is exactly right, the motion will build until the glass breaks.
Wow. So, as we would expect, the speaker breaks the glass nearest to it. And immediately we see a crack that goes all the way around the whole bottom of the frame. I'm going to play that back again. This is where the initial fracture happens, right nearby the speaker. And in about 3 frames, and this is 3/10,000ths of a second, we see this crack go along the bottom where the glass gets thicker and come right back up to the top where it's thin. So if we follow that a little more, this piece has just fallen off, but it doesn't in some sense even know that it's fallen off from the rest of the glass. All of the glass was shaking at about 300 hertz, 300 vibrations per second, And this piece is still doing that. You can see the corners of the glass still flexing as if they were influenced by the speaker, but the speaker is way too far away now to have that influence on this piece. It just has the leftover inertia. And we see that in all the pieces here, even along the top edge of this glass. This piece of glass is not resonant at that frequency anymore, so it can't get energy from the speaker, and all that we see shaking is the leftover energy from what the speaker gave it in order for it to break.
So, if you thought that glass couldn't bend, think again. Time warping changes the way we see the world because it makes the invisible visible.
So the idea is the wine glass has a natural frequency that it sort of wants to vibrate at. Okay, so maybe it's whatever, 400 hertz. All right, so if you are able to sing and create a note that has that same frequency of 400 hertz, then the two frequencies match. And what will happen is every time a new compression of air hits that wine glass, it'll vibrate a little bit more and more and more until eventually the vibrations are so big that it breaks the glass. All right, it's the exact same thing as pushing a kid on a swing. All you're doing is you're replacing the person pushing the kid on the swing with sound waves pushing the wine glass. Okay? And then one last sort of weird example is rocking a car out of the mud. If you want to push your car out of the mud, you got to get it going forwards fast enough. And so what you do is you push it forwards, you wait for it to rock back a little bit, and then at that exact right moment, you push it forwards again. Okay? Very similar to pushing a kid on a swing. All right, so that's resonance. Write it down, and we'll do more examples in class. But this at least gets the writing out of the way, and I can give you guys the demonstrations in class. All right, and hopefully I was able to edit in that wine glass, the guy breaking the wine glass. All right, so that is the deal with resonance. All right, so that is the end of that. We've got one other quick topic that we need to talk about, which is not on the screen, right there, interference. All right, interference doesn't really have anything to do with resonance. It's its own separate topic. It occurs when two waves cross paths. All right, and it turns out there's two types of interference. There's what's called constructive interference and destructive interference. Constructive interference occurs when two crests or two troughs meet. And the resulting wave, when that happens, when you have crests meeting crests and troughs meeting troughs, the resulting wave has a bigger amplitude. All right, destructive interference is the other way around. That occurs when you have a crest meeting a trough. So there you've got sort of a positive amplitude meeting a negative amplitude, and they kind of cancel each other out, and it results in a wave with a smaller amplitude. All right, this is probably easiest to just show you an example of. So let me bring up this applet here. Okay, so what we've got here is two wave pulses. Each of these little boop, boop, each of those guys kind of represents a crest of a wave. All right, and I've got it paused right now, but what's going to happen here is these two wave pulses are going to travel towards each other. This one is going this way, this one is going this way. So when I click pause, they're going to move towards each other. And I've got it in super slow motion, so it's going to happen very, very slowly. But what I want you to watch is what happens to the amplitude. All right, so what I'm going to do is I'm going to grab this little red line down here. All right, so right now, the amplitude of one individual pulse is this distance, right? That's your amplitude. Okay, and so what's going to happen is this crest here is going to meet with this crest here, and you can kind of think of it as this has a positive amount of energy, this has a positive amount of energy, so when you add them together you get an even bigger amount of energy, and so it should give us a bigger amplitude. All right, so let me unpause it here, and let's see what happens. So the two waves are, oh no. Okay, now they're moving towards each other. The waves are moving towards each other, and boom, right there, we had that moment where they overlap with each other, right? And look what happened. So right now, my two crests have crossed paths, and our resulting amplitude is basically amplitude plus amplitude, right? You've got the amplitude from the first wave combining with the amplitude of the second wave, and then what happens is the two waves go on their way. So the wave that was originally going this way will just kind of continue over this way, and the one that was originally going this way is going to continue this way. So they pass through each other. They don't bounce off of each other. All right, so, and there they go. They just continue along on their way. Okay, let me do it again. All right, I want to do it again just because I feel like the beginning of that last one got messed up. So once again, here's the deal. You've got wave pulse A going this way, wave pulse B going this way. They're going to overlap each other. Here we go. I had them going the wrong way before. And so you get an increase in amplitude. All right, so that is called constructive interference. I should note really quickly, too, this would also work if you had two troughs meeting each other. So let me do that real quick. Okay, so really quick, here's the same thing, but this time it's two troughs. So we've got this trough going this way, this trough going this way. Let's grab our little marker here so we can mark our amplitude. And when they cross, you're going to get a sort of a deeper trough, because now we've got a negative energy plus a negative amount of energy gives us an even bigger negative amount of energy. And there you go. All right. So the next thing we need to talk about is what's called destructive interference. Destructive interference occurs when you have a crest meeting a trough. Okay, and the idea is they kind of cancel each other out. So let me show you that. Oh no. Okay, so now what we've got is a positive amount of energy in this crest over here, and it's going to collide with a negative amount of energy from this trough. And this is a little sloppy calling it positive and negative amounts of energy, but the displacements, I guess, are what are canceling out there. So anyway, so what's going to happen here is they're going to cross paths, and there's going to be a brief moment where our crest is completely on top of our trough, and they completely cancel each other out. All right, so I'm going to let it go here. I wish I had, oh, I do, duh. All right, so let me sort of mark. There's our maximum amplitude. And same thing down here. That line down there sort of represents our maximum amplitude. Okay, so let me unpause it and watch what happens. So they're starting to overlap, and boom, there's a split second where they completely cancel each other out. I couldn't have paused that at a better moment. All right, so what's happening right now is this wave here is there, this one is there. You've got your positive and your negative, and they completely cancel out. And if I unpause it, you can see that they kind of pass through each other again and just continue along the way they were going before. Okay. I'm going to let this keep. Oh, no, that won't work. Okay. So anyway, there you go. Destructive interference. All right. And so, as I said, the result is that with constructive interference, you get an increase in amplitude. Oh, you get an increase in amplitude, and with destructive, you get a decrease in amplitude. All right. I think that's it. Is there anything else I need to tell you? I think we're good. Cool. All right. Hopefully I've edited in a video.